Dear students, good evening and welcome to the class. Today we will be discussing about Rolle's theorem. We will see the proof. Before that, we will see what the theorem is saying about. The statement is like this. The function is defined on the closed interval a comma b. The function is defined in the closed interval a comma b such that the given function is continuous in the closed interval a comma b. Second condition, f of x is differentiable in the open interval a comma b. And the third one is f of a is equal to f of b. If all this happens, then there exists one value c in the open interval a comma b such that the derivative at that point will become 0. We will go to the proof part. We will start with, since f of x is continuous in the closed interval a comma b. From where we got this? It is given. Okay. Now we can say, since f of x is continuous in the closed interval a comma b, f of x is bounded. How we got this? Because of, since theorem says every continuous function defined over the closed interval a comma b is bounded. That means any function which is defined in the closed interval a comma b is bounded. And now we know that the function which is bounded will have two values. One is called supremum, that is the maximum value, of the function f of x. One more value it will be having is infimum, that is the minimum value of the function f of x. And let that supremum value we take it as capital M. This infimum value or the minimum value we take it as small m. That is capital M is equal to the maximum value of the function in the closed interval a comma b, and small m is the minimum value of the function in the closed interval a comma b. Now there are two possibilities. There are two possibilities. There are two possibilities, such as, we'll take as case 1, m can be equal to capital M, small m can be equal to capital M, or case 2, they both are not equal to each other. We'll take up the case 1 first. Case 1. When small m equal to capital M, this implies the function is constant function. The function is constant, that is f of x is equal to constant. How can we understand this? Using graph. Suppose I have a graph like this. So this is the maximum value of the function. This is maximum. Okay, this is the minimum value. But what if I write like this? That means here small m is equal to capital M. Both are equal. Okay, so this kind of functions are called as constant functions. As an example for the constant function, suppose you have, let me write this as example, f of x is equal to 2. That means you will draw a straight line like this. For any values of x, any value change x, the function will remain same. It will be unchanged. Therefore, now come back to the proof part. Since both are equal, the function is constant, that is f of x is equal to constant, and when we take derivative, the function value becomes 0. That is f dash of x is equal to 0. At x is equal to c, f dash of c is equal to 0. This is in this case the theorem is proved. This was the condition we had to prove, so we have proved. Now this is our case 2. When m is not equal to capital M, this means what? This means all these values are not equal to each other. All these values are not equal to each other. Okay, now since we have two supremum and infimum. This is our infimum. This is our supremum. I can write any one of them are not equal to each other. We will take up supremum because since we have one theorem which says every function which is continuous, which is continuous in the closed interval a comma b, attains its supremum. Attains its supremum. This is one theorem statement. That is there exists one value c belonging to a comma b such that at that point the function value will become the maximum or the supremum value. I am reading out once again. This theorem says every function which is continuous in the closed interval a comma b. We also having f of x as the function which is continuous in the closed interval a comma b, therefore it attains its supremum. That means what? There exists one value of c in the closed interval a comma b such that at that point the function value will become its supremum. That is here m is supremum. Also f of c is supremum. Why? Because since they are equal to each other. We can say m is also supremum, f of c is also supremum. Now since we have taken c as the supremum over there, c as the supremum, let me write in another ink. Since c is only supremum, I can write plus or minus h on both sides, plus or minus h. Since this is our supremum, here is this. Let us take the function only. Since I am saying f of c is itself, this is only supremum. So this can be f of x should be less than f of x should be less than f of c. So irrespective of now any changes in the function, this will be remaining as it is because f of c is supremum. So I can rewrite this part as it like this. I can take on the left hand side. So now I can divide throughout by plus or minus h. What do I get? C plus or minus h minus f of c whole divided by plus or minus h less than or equal to 0. By looking at this, we can say if I include limit h tends to 0, this will give me the formulas of left hand derivative and the right hand derivative less than or equal to 0. Since these are plus or minus, I can split this in terms of f of c plus h minus f of c by plus h. Here also I can split like limit as h tending to 0 f of c minus h minus f of c by minus h. Now we know this is the definition of right hand derivative, that is r f dash, the point is c over here, r f dash c, and this is the definition of left hand derivative, that is L f dash of c, and both are this is less than or equal to c 0, this is greater than or equal to 0. This implies right hand derivative is equal to left hand derivative, implies r f dash of c is equal to L f dash of c, and this will happen only when f dash of c is equal to 0. So by both of this I can write f dash of c is equal to 0. So with this we can conclude that there exists a point C belonging to a comma b such that f dash of c is equal to 0. Hence the